Okay. Today we're very happy to have Gregor from Princeton University to give us about his seminar. He got his PhD in Nantes, France in 2022, and now he's a postdoc in Princeton University, working with Trin. He focused on the modeling of heavy ion collisions with the evolution of conserved charges. Today, he will give us about tracing the band number in realistic isobar collisions the week. Yeah, please.
Thank you so much for the nice introduction. So, yeah, my name is Grégoire Pillon. I'm working at Wayne State University, and today I will talk about tracing the baryon number in relativistic isobar collision at RHIC. I do this work with Junction mainly, and Bjorn and Haki Komonai. So, the main question of this talk, and I wish we will have some answers at the end, even though I think it's quite complicated, but still, it's what carries the baryon number. And the previous question from that is, how do we build a baryon from quarks? So if you have 3 quarks, how do you build a baryon from that? So we basically associate baryon number 1 to a baryon made of 3 quarks. But the fact that we associate 1/3 of baryon number to each quark, this is an assumption. And this is very easy for the thermodynamic calculations, for instance. It's super simple to calculate. But there is other possibilities. And in particular, there is this string junction model that we will discuss in this talk, which consists in thinking of the baryon number that this baryon number would be carried by a junction here in the middle, made of gluon, a 3-vertex gluon actually. And we want to try to see if we can distinguish between those two situations experimentally. The string junction doesn't come from like imagination. It's actually the most simple way to build a baryon from 3 quarks, but which also respects the local gauge invariance. This is basically made by having these anti-symmetric operators on some Wilson loop here, which connect all the quarks in the middle here in what we call the junction here. And if we calculate the baryon number related to that operator, we see that it's actually carried by this. It will follow this. In this talk, I will say trace or carry in the same way, but the idea is that the baryon number will follow this 3 gluon vertex here instead of the quark individually. And in his paper in 1996, Carthy said that we can see that experimentally in the baryon stopping in central PP and AA collision. And in this talk, we will be concentrated on AA collision and especially on the isobar. So what do we see now in terms of baryon stopping related to that question? So in the case of the baryon junction, the baryon stopping will be shifted differently. So basically, first of all, the baryon stopping for me would be the amount of baryon number that stays at midrapidity in the collision. That's what I call the baryon stopping here. With the junction, we have 2 situations. So let's imagine that here on the left, you have a nucleon, and you have also a nucleon on the right here, and they have quarks. Those 2 quarks, they will, after the collision, they will form a string. And as the 2 nucleons continues into their direction, the string will break at some point. And the junction here can, if it connects 2 quarks inside the nucleon, for instance, it will put the baryon number, because it will be connected to this quantity here, to the nucleon. It will stay attached to the nucleon. And then, as a function of the rapidity, we will see a baryon number picked around the nucleon beam rapidity here. But on the other hand, we can have 2 splittings with the strings, and then you have 3 free quarks in the middle, and they can form a junction in the middle, and then the junction will try to put the baryon number towards the middle. And this is what we want to observe, that the number of baryon, the net baryon number here at midrapidity will increase due to this phenomenon. What we observe experimentally for now is that if we show the net proton number here, which is a nice proxy for the net baryon number, in gold-gold collision, as a function of the rapidity loss, which is connected to the energy at star, and we show the value of the net proton at mid-rapidity for all of these energies or rapidity loss, we see that it nicely falls on an exponential decrease. And this exponential decrease, we can extract by a fit the exponential decrease coefficient, alpha, and it's equal to 0.61. And we see that if we do that for, so this is for most central collision, but we can do that for any selection in centrality, and we found quite the same number. So basically, the baryon number is stopping in a consistent way between all of these centrality cuts.
Are those for the same energy?
Sorry?
Are those at the same colliding energy or different colliding energy?
So different energies.
That's different
energies, yes. Yes, okay. Absolutely. So this is the rapidity loss is the difference between the beam energy and the beam in the center of mass. So basically, this is where the nucleons will be, or the two receding pancakes, and this is the center of mass. So the higher the energy, the higher this we go in this direction. So here it's LHC, and here it will be like smaller energies.
Okay, but in principle, you can also measure this at a given energy, but changing the rapidity window, right?
Yes.
In the high energy region.
Yes.
For example,
like
if you can do that at, I don't know whether you have the coverage of large rapidity coverage, but in principle, if you do, I mean, if you have, you can do that too.
Yes, I think so, but I think this is simpler to do that like that, I guess. It's just that because now instead of having one fixed two peaks and then opening the rapidity window, we keep the rapidity window fixed and we change the position of the peaks. So, I mean, this is exactly, I mean, this is complementary, so to say. So I agree, and that's a nice point. Thank you. So indeed, this can be understood as this exponential decrease here. Basically, this exponential decrease of the baryon number is given with this coefficient. And this is actually compatible with the junction picture, because in the junction picture, you have either single junction or double junction, and the situation are represented here and here. But for the single junction, you will have only an exponential decrease with a coefficient alpha, which is calculated from the RHIC theory, given by 0.5, which is kind of close to 0.6. So people were thinking that maybe this observation that we do experimentally here is connected to the baryon junction for this reason. In the case of the double junction, you actually have a flat curve. So now, what can we learn from the isobar collision related to the baryon stopping? So the isobar collision, for first of all, what is it? It's collision between ruthenium and ruthenium, and zirconium, made at RHIC between 2018 and 2021. And they share the same number of nucleon A, 96, but they have a different number of proton here, 44 and 40. And this allows to compare not only to measure the baryon stopping, but to measure it in a very precise way using the electric charge stopping too. So basically, we can do some ratios. That's the point of the isobar, generally, doing some ratios. And then we can cancel some uncertainties and some systematics, and we can reach some much better precision, especially in the electric charge. But for our case, it's just that in this situation, this system, we can compare the baryon stopping to electric charge stopping. And this is very interesting for us because we want to have a baseline of what is the baryon stopping, what is the stopping if everything is carried by the valence quark. And if we suppose, this is a supposition, but it's a reasonable one, that the valence quark carries the electric charge, or that the electric charge stays attached to the nucleon, the proton actually, then we can say that that if we see the same stopping for both the baryon and the electric charge, then we are in an equal stopping situation, and the valence quark may carry or the nucleon may carry the baryon number. But if they stop differently, if the electric charge and baryon number, they stop differently, then maybe there is something, an extra stopping mechanism for the baryon, or less stopping mechanism for the electric charge. We will not know why, but for the baryon, we expect that there would be an increase of the baryon stopping. And this increase of the baryon stopping can, well, come from the baryon junction. And that's why we want to try to understand here in these simulations, because we want to, this measurement has been done experimentally, but we want to try to understand it fully before concluding anything. So what about the measurement? So the measurement has been done by STAR. Here I show you some preliminary results they have for this isobar collision at midrapidity. They measure the ratio between the baryon number measured at midrapidity divided by the electric charge difference between the ruthenium system and zirconium system. So this is actually a measure of these two situations. You can think of this like that. I will come back into this ratio into details after, but still, if it's 1, we are in an equal stopping situation, and if it's different from 1, then we are in a different stopping situation. And if it's bigger than 1, this means that we have excess baryon stopping. And this is what we observe experimentally as a function of n part for all the centrality here. So this means that we have something that is going on, which is an extra mechanism for baryon stopping as compared to electric charge stopping. And the question we ask here is this a sign of the string junction?
Yeah, but before you said that the exponent alpha is independent of the centrality. So from that, should I not conclude that the baryon stopping is independent from the centrality, and thus the difference here comes from the charge stopping?
No, not really. Okay, that's a very good question. No one asked me, but that's a very good question, because here you see that there is a decrease of the curve, indeed. And what you expect is that it's independent of the centrality, so it's flat. And I agree with you. And we will see by the end of this talk that this is actually due to the nuclear structure of the ruthenium and the zirconium, which plays a very important role into this measurement actually, and this is part of my talk. So thank you for the question. Okay, so to do these simulations, to understand that, I will use the IEBE music framework, which is an open source hydrodynamics plus hadronic transport hybrid framework, and especially so it's composed of many stages. First, the initial stages, then we have a hydrodynamic. Then we have a particularization using the ISS code, then afterburner URQMD, and then some analysis. But I will mainly focus on the initial condition built with the 3D-MC Glober and the conserved charge evolution for this work. And let's directly dive into the building of the initial condition. And for this, I really want to show you things very schematically, because we had many questions about the way we do that. So I present you this in a very schematical way. So basically, imagine that you have the two nucleons that are colliding during the collision. So right after the collision, in the 3D-MC Glober model, we have a scheme to deposit energy density, momentum density, and the conserved charges on what we call strings, which are basically a connection between a parton from this nucleon and a parton from this nucleon here, and say that you have one baryon number here. So this is a proton, basically. So we have a probability then to associate this baryon number to this nucleon. So this is the rapidity at which the projectile is. Say this is the projectile. So the baryon number will stay at this rapidity with a probability which will be given by 1 minus lambda x, and I will explain in detail what we call lambda x here. But it will have also it has also a probability to jump onto the string with a probability lambda x. And if it jumps on the string, then it has two possibilities. First, it follows the single junction scheme, which is an exponential decrease, as we saw. So basically, the distribution of this baryon number position on this string will be given by this formula, which is simply an exponential decrease normalized. Or it can also be done by the double junction, which is a constant. So basically, the distribution will be flat. The baryon number can be deposited anywhere in the string in the middle. But in this work, we don't consider the double junction, and we only consider the single junction. This was a choice because it was easier, and this will not be seen in our observables, basically. It's more something that you can see into the V1, V2, or the flow observable, basically. So in the end, we have a probability distribution of putting the baryon number that we have on the nucleon somewhere in the nucleons or somewhere in the string. And it follows the single junction prediction from D. McCarthy. So now I want to explain what the lambda x are in this formula. Basically, x here refers to both baryon number and electric charge. For the baryon number, this can be easily understood by the baryon junction. So we have a physical motivation behind writing this lambda b. Sometimes it follows the baryon junction distribution. And if we take a look at the net proton distribution as a function of the rapidity loss also for Gold most central collision, we see that having lambda b equals 0.2, it fits the data much more. And the same happens for alpha. So sorry, here it should be just alpha. Anyway, it's better. So if we take lambda b equals 0.2, it fits the data better. So this is what we will take in the remainder of this work. And basically, this has to be understood as 20% of the time, the baryon number which is on the string will follow the exponential decrease. And 80% of the time, it will stay on the nucleon. But now we have also this for the lambda q parameter, which will be associated to the electric charge, because we want to have a way to measure how the baryon number and the electric charge number stoppings can differ. So basically, this is a free parameter. There is no physical motivation behind it. I mean, the electric charge doesn't stop by the baryon junction. This would make no sense. But still, here we use it as a free parameter to have these two situations. If lambda q is equal to lambda b, then we have equal stopping because the two baryon and charge will follow the exact same probability distribution on the string. And if they are different, we have different stoppings.
May I have a question?
For the initial, yes?
Just want to ask why the electrical charge has the same formula as the baryon charge stopping.
This is absolutely, as I told here, is absolutely a random choice. It's just that we don't want to complicate ourselves. As there is no actual constraint from experimental data about the electric charge stopping, because it is very, very complicated to measure. I know that there is some work trying to have an intuition on what is going on with the Bremsstrahlung, for instance. But this is a very complicated measurement, and I don't think that there is a lot about that. So basically, we have no physical constraint on this lambda q parameter. So here is just a way to measure the two stoppings, basically. The ratio between the two stoppings, sorry.
Okay, another question. For non-zero lambda q, which means there is some electron charge junction, similar structure. I mean, how to understand the non-zero lambda q?
So what you can understand, if you think about the physics, So in the physical picture, it makes no sense. There is no baryon junction for lambda Q, but in our model, this would just mean that you can do the same thing. Instead of the baryon charge here, you can have an electric charge here, and then you just allow it to fluctuate in the string according to this distribution, basically. So this is just a way to deposit more electric charge at mid-rapidity or not. So this is something on which we can play, like something we can, a little parameter that we can tweak. So we can have more or less electric charge at mid-rapidity in these runs. But this is not constrained by a physical picture. And if we take a different value for the electric charge, this is totally fine. I mean, it's just that then the interpretation lambda Q equals lambda B is different, basically. Did I answer your question, or?
Okay, yeah, thank you.
Thank you. So we have also a scheme to set the shape of the nucleus that we have, because this is important here. We have ruthenium and zirconium, and they have some kind of structure. So we have Wood-Saxon potential, which allows us to set the nuclear structure and the neutron skin here. It's given by this radius here, for those who are familiar. But what you have to have in mind is that you can play on this shape, the oblate shape here, or this more elongated shape in the longitudinal direction, or transverse, whatever in which direction you think, or this triangular or quadruple, everything. But here I sum up all the numbers that we have for ruthenium and zirconium. These come from the density functional theory calculations, so low energy physics. And here, what we see is that they have pretty similar radius, almost the same diffusiveness, and they have slightly different beta 2. So basically, the ruthenium is more like that, and beta 3 for zirconium is like that. And we had two extra parameters to the Wood-Saxon potential, which are dA and dR, which are the difference between the diffusiveness of neutron and proton, and the radius of neutron and proton. And what we see is that the radius for neutron is larger than the radius for proton for the zirconium, which means that we have a neutron skin here. That's what I refer to by the neutron skin. And just to give you an intuition, I just draw you some wonderful ruthenium and zirconium nucleus here. So basically, the ruthenium looks like that. Here in the middle, it's violet, so you have both protons and neutrons. And here you have more neutrons on the side. And the zirconium, it has a larger neutron skin, and it's more triangular shape. So here is an example of what kind of initial conditions that I get after doing all of that. And here, for instance, for the baryon number and the electric charge number distribution as a function of rapidity here, for the case lambda Q equals lambda B equals 0.2 equals stopping. For the most central collision, we simply have this kind of curve. So basically, the number of baryon is close to be the same, because both ruthenium and zirconium have the same A number, but they have a slight difference due to the difference in electric charge here. And just to give you an idea of what this lambda Q parameter does, which is our free parameter in this study, it simply removes some electric charge here at beam rapidity and put it at mid rapidity. That's the only thing that it does, basically. And it actually does the same for the baryon number. This is exactly the same idea. If you increase the lambda Q parameter, more will be in the middle and less at beam rapidity. So now we want to...
Can I have a question?
Mm-hmm.
Yeah.
Yeah.
So you see dNB dy, so in your model calculation, just to count all the baryon, the proton, neutron, lambda, or just the proton?
Okay. Yeah. So here it's at initial stage, so we only have yeah, whatever. So I will just answer the question. We calculate the baryon number by net proton plus net neutron, and we calculate the electric charge with the proton the kaons and sorry, and the pions. Yes, yes, that's the only particles we use.
And all the particles are just the proton, or
Sorry.
I mean this bar is in your model calculation includes only the proton or the proton neutron, or all of them.
Ah, yeah, proton and neutron. The baryon number is calculated by protons and neutrons.
And for charge, it's the pion proton.
Yes, proton, kaon, and pion. Yes, exactly.
Okay.
Thank you. Yes, so now we want to put these initial conditions that you have here into the hydrodynamic evolution and let it evolve. But in most of the hydrodynamic codes that we have a constraint between the electric charge density and the baryon number, baryon density during the evolution, which is this one. 0.4 doesn't come from nothing; it's just A over Z for most of the say lead or gold. This is close to 0.4 A over Z. So this is just that the baryon number will evolve, and then the rho Q will always stay like that. It's just a simplification. But in our work, this is not possible because if we have a slight difference between B and Q at initial stage, and we put this into the hydrodynamics, and then we impose this constraint, then the ratio will always be 0.4, and we'll see nothing. So the idea is that we remove this constraint, and for this, we had to implement the ideal evolutions of the conserved charges into the music hydrodynamic evolution. So basically, this simply consists in taking in adding this current for the conserved charge. This is at ideal level. We don't have diffusion. This is something that we think of adding in the end because this is kind of important for this kind of study. But here is a presentation for ideal level hydrodynamics results. But most importantly, now B, Q, and S current can evolve independently. And then we remove this constraint and we can see what happens at the initial stage if this stays at the final stage or if the hydro has a large impact on it. And in line with this, now that we have 3 conserved charges, energy and momentum in our hydrodynamic, we needed a 4D equation of state that can be calculated for any particular situation of B, Q, and S. And for this, we use NEOS equation of state, which is based on the lattice Taylor expansion at finite chemical potential, here up to order 4. At smaller temperature and biochemical potential, or all other potential actually, this is the pressure is given by the hadrons resonance gas calculation, and the connection between those two, the matching is simply done by some hyperbolic tangent, as you can see here nicely, the hyperbolic tangent in T and mu here. So if you are interested here, you can see the range that we have for the mu Q, mu S, and mu B. But the most important things to take home is that there is no assumption on the relation between the conserved charge density. And so the B to Q stopping ratio can be studied into this novel framework of hydrodynamic with music codes. And just to give you an example of what I'm talking about, this is just an example of a hydrodynamic run that I did. So I integrate everything into the transverse plane, but this is 3D hydrodynamic. And we have here rho Q, so the electric charge density as a function of tau and eta. So tau is in this direction. And here we have rho B, which is the same for baryon number. And we take a look at this constraint multiplied by tau to see something, because there is actually a dilution factor. And you see that it's not always 0 in our simulation using this 4D framework, so to say. And especially at midrapidity, where we are interested, we see that it's negative. So we have an excess baryon here, which can come from our scheme from the baryon junction. Yeah, so yeah, that's what I wanted to say with this. Now we have the identified particle PT. So after the hydrodynamic, we have a phase of particleization, and then we have an afterburner, and then we measure the particle at the end. And what we observe is that we have, for the pion, kaon, and proton, if we compare to the identified particle PT spectra directly given by the star measurement for the isobar, ruthenium and zirconium, is that we quite agree with the results for proton, kaons, and pions, which are the main particle which serve for the calculations of B and Q at midrapidity. And we see that we fairly nicely reproduce the proton for a small transverse momentum here. But we have some difficulties for very high PT, which is something that I think we always have in this kind of hydro. And we are quite okay with the rest of the particles. So this is just for you to see that we are not completely out of tune with the experimental measurements. Now I want to, before discussing the results, I want to go into this detail about understanding what is the baseline, what do we expect with the measurement that we did and the simulations that we have. And for this, I want to come back to the definition of this ratio that we have in this results from tau. So it's basically B over delta Q times delta Z over A. The B here is defined as the net-baryon number measured at midrapidity in this range, plus the net-baryon number from zirconium, ruthenium plus zirconium, divided by 2. The reason why is they do that is simply because this can increase the statistics. As you can think, you have twice as much as if you only consider the B or the ruthenium or the zirconium. The delta Q is given by the same measurement, but for the electric charge at midrapidity, and the difference is ruthenium minus zirconium. And delta Z over A is just the difference in Z, which is 4, between the two isobar, and A, which is 96. So it gives simply a number, 0.0422. This is just a number. So the most important things to understand here are those two quantities here. And this actually comes from the conservation applied, the charge conservation, applied at mid-rapidity. So you know that in heavy ion collisions, we have the global charge conservation. So basically, if we have a total number of baryon,
can you go back to last slide? I try to understand what is the definition of delta Q here. The NQ is the net charge.
Yes.
What is is that right?
Yes, you're right. So this is the net baryon number and the net charge measured at mid rapidity. Maybe I was
at the middle rapidity, but you are. Then I don't understand. I mean, this is you are colliding zirconium with zirconium, right?
Yes.
Not rubidium with zirconium. So why?
Yes, absolutely.
You take the difference between two different isotopes.
We have different charges.
What?
The two isobars have different charges.
I know, but they're not colliding with different isobars.
No, but if you collide the pair with the higher charges, you would expect to have a bigger net charge at mid-rapidity than if you can collide the pair with the lower charges.
So you are doing comparing the difference or the ratio? As the same.
So this is. Yeah, so this is, I think that there is a quite something.
I thought the net Q essentially is the net charge in the collision in the central rapidity, right?
It's the difference of the net charges.
The difference
of the net charge in the ruthenium or ruthenium collision minus the net charge.
Is the difference between two different nuclei, two different collisions.
Yes. Okay.
Yes, absolutely. Yes. And this is actually something very interesting because, you have to be sure that the selection is done properly, and we will have a discussion about that if you want. It's like if you this comes from the system, and this
baryon is not different. It's the total.
Yes.
The
baryon number is not different,
right?
Yes, absolutely. But the electric charge is different. And then when you take the ratio, basically, when you take the ratio between those two, you can have some cancellation, and even into that, you have some cancellation. If you want, we can discuss at the end. I have a slide which describe how the experimental, I mean, at star, how they calculate those two numbers. If you want, if you're interested.
Okay, I'm misunderstood. I thought that delta Q is actually just net charge in any collision, but you're talking about difference between
no.
two different isotopes.
Yes. Yeah. So basically, this is really to cancel some systematics between those two. And yeah, I said the. Oh, sorry. Yes. Okay, I will describe something now.
It's very
So,
strange way to
yeah.
define it.
No, I will explain why is it this. So basically, if you have the global conservation of the charge, you have A over Z or Z over A, and it will stay the same at the end of the collision if you don't lose particle in the void. I don't know, but if everything is here, you have the charge conservation. Now, if you just apply this, but at mid rapidity, you say that whatever is deposited at mid rapidity stays at mid rapidity, and it follows the global ratio. So basically, if we have Z over A, we will have also Z over A ratio at mid rapidity. This is what applying the conservation at mid rapidity means here. And then you will have a relation between the baryon number you have at mid rapidity and the electric charge you have at mid rapidity, which is just electric charge equals Z over A times B. That's it. And then you can differentiate this relation between those two systems. You just consider that this delta is between the ruthenium and zirconium, and you simply obtain this formula. This formula is saying that the difference in baryon number measured at mid rapidity between ruthenium and zirconium will be connected to this value with that coefficient. And here it's the baryon number measured for ruthenium, and we see the delta Z here. So basically, this has to be understood as, we call it R2 in this study, that if this ratio is close to 1, the ratio between this quantity, and this quantity, if this is close to 1, then the charge conservation is respected in the mid-rapidity range. The global charge conservation applied to mid-rapidity is respected. And if it's larger than 1, or it can be smaller than 1, then we have more baryon than we expect, because this is at the denominator. So we have more baryon than we expect. And if it's smaller than 1, we have less baryon than we expect. And this is what, where does that come from? But now you see that there is a difference between how this is defined with the star measurement here. Do you have a question?
No, okay, go ahead. I was just about asking. I think you're just about to explain what I wanted to ask. Go ahead.
Yeah. Okay. Yeah. So basically, there is a difference between the star ratio, and I'll explain what is it. So you can rewrite this ratio that I call R2 here as a function of two other ratios, which are R1 and R0. And R0 is simply the net baryon number ratio at mid rapidity, so B ruthenium over B zirconium. So this is really you measure the baryon at mid rapidity, and you can see a difference between those two systems, even though they have the same total number of baryon, because we are only looking at mid rapidity. For some reason, it can be different, but anyway. And what I call the Ruby ratio is R1. And experimentally, they do some nice selection into this and some nice correction also of their selection, and then they have this constraint on, like R0, so the baryon number for ruthenium and zirconium measured in the same rapidity window is the same for them. Like they assure that, and then this ratio here, R1, is equal to the star ratio, because then B ruthenium is the same as B zirconium, and you have this is just B ruthenium plus B zirconium over 2. So this is the mean. So you have here what they call B, and that's it. Oh, I'm sorry, I forgot to divide by delta Q here, but there is a divided by delta Q here. So basically, the star measurement, the star ratio, is simply so to come back here, it's simply this part here. when this is equal to 1. And now, what happens in the simulation? So what we do in the simulation, depending on the selection, I can select it in the exact same way as star or not. I can choose it. So we don't have this in general. So we have to take into account this other term because we have a corrections due to this term here. And then our ratio that I call R2 will deviate from the star ratio here. And this is what I want to tell you here. This message is that I can show you the R1 here ratio, the Ruby ratio, calculated into my simulation, but it can differ from the star ratio because we have certainly some selection or things that are different. And this is what I call identifying the baseline here. So yeah, this is the idea. Then R1 can be different from the star ratio if we have this quantity which is not absolutely 1. So now I want to take some time to disentangle all the contribution from everything and to understand what is going on. So these are some results that I showed you, the first results. So this is at initial stage, so just for the 3D MC Glauber model. And I show R0, so the ratio between the baryon number for the two systems, R1, which is closer to the star ratio, and R2, which is the exact charge conservation at midrapidity, as a function of n part ruthenium. For this situation, where the ruthenium and zirconium are considered to have the same nuclear structure. So basically, protons and neutrons are evenly distributed inside a circle, or a sphere, actually. And what we observe is that this ratio is close to 1, but it's not absolutely 1. And this, we understand this as that the baryon number ratio impacts okay. So we understand it as a way that we select things because we impose the selection on the charge particle in our model. And then this gives us a centrality class. And this can be different from zirconium or ruthenium and can be different from electric charge and baryon number. You can have some different distribution into that. And this comes into the game in our simulations. But still, it's very close to 1, actually. It's not very large effect, like it's the percent effect. So that's okay for this kind of situation. Now, if we take a look at the ratio R1, which is the ratio closer to star measurement, we see that they will have some kind of structure here, non-monotonic structure. And if we take the exact charge conservation, which will take into account this selection bias that we have and that we can try to work on, it will be more flatter and closer to 1. And now I want to show you that if we consider different nuclear structure for the ruthenium and zirconium, but we have also no neutron skin. So we don't consider the neutron skin, but we have different nuclear shape. And we see that here we have like a larger impact on this ratio of baryon number at midrapidity. And this is due again by the selection. So basically, when you collide those two things, even if on average it should be round, basically, you can have some difference because even for more central collision, the overlap is absolutely not complete. I mean, if you put that on that, you don't have absolute complete overlap. It changes something into the selection, so you can mix things up, and then you get that curve. And this has an impact also on the ratio, which is close to star. And you see that the decrease that we were talking about before in our simulation comes from that, basically. So you see that there is a decrease where something that we expected to be flat. Here in the exact charge conservation ratio, you see that it's flat, as expected by the fact that by the other measurement, which shows that it's centrality independent, this kind of measurement. So the nuclear structure impacts the ratio R1, the star ratio. And now if you consider...
There is
a question on that.
Yeah. So on the first ratio, the R0, so you say that the star selects the baryon the baryon number between the two isobar to be same in the centrality classes. So what exactly do you mean? Which selection?
Okay, so I'm not a specialist on that, but the idea is that, which I think is that they have some way to select the centrality class basically in a way, and they have also corrections on this selection. I can point you to the paper, and I'm not a specialist on that, but they have a correction on this selection that ensure that we have in each centrality class that we have something like B ruthenium equals B zirconium. But I'm absolutely not sure how is it done for now. And I need to take a look at this in detail because I want to implement that in our model, to be honest. But yeah, I referred you to Zhangbu if you want, from STAR, if you know him. He will explain that to you in details, I guess.
Okay, yeah.
I'm sorry, I cannot answer this question in detail. Yeah, so, and that's the reason why we don't have it in this work. I don't fully understand how is it done. So yeah, for now, we just correct it with another ratio, but that's the idea. Okay, now if we consider that we have also the neutron skin involved, so we have more neutrons on the side here, then we have another impact, and especially at larger, at large impact parameters, so to say, or small n parts, because then you only collide neutrons with neutrons. So you expect that there is a decrease of the curve, and again, decrease of the curve related to that, because remember that the electric charge is at the denominator, and the electric charge is concentrated here, basically. And here you see what I want to show you here is that here we disentangle the contribution from, in our calculation, not the star measurement, but in our calculation, between the actual nuclear shape and the neutron skin. And you can see this effect here in the exact charge conservation ratio by this curve in red. This is the net impact from the neutron skin. So this is also very, very interesting for us because maybe with this observable, we can do some nuclear structure measurements. But for now, it's really interesting to understand that part of our decrease is coming from the nuclear shape and also the selection bias that we have. But in the star measurements, the decreasing is only coming from the nuclear structure, if we want to think about this, because they have this selection, which is much better treated than us, so to say. So that's what I wanted to say here. No, you need to stay there. So now I want to show you some comparison of this R1 ratio that we have on the simulation with the star measurement. And what we observe is that for the two situations, first the equal stopping. So when lambda Q equals lambda B, electric charge and baryon number have same stopping. We see the green curve here as a function of n part, and we see that it's smaller than 1. And now if we say we put lambda Q equals 0. So this has to be understood that there is no extra stopping mechanism for the electric charge, but there is an extra stopping mechanism for the baryon number coming from the baryon junction. Then we see that the results are much closer to the data point. So for this star ratio here, this is at initial stage, sorry. And here I show, just so you have it in mind, that if we want to compare what is comparable, if we had same centrality selection, our curve would certainly look more like that. So which means closer to 1. So this is the exact charge conservation. And for the two situations, so we still see an increase here. So there is something which is going on, but certainly it is not. It's in between this curve and this curve, and this curve. Sorry. So I show the two curves here. This blend curve here is this one, basically. So yeah, and the measurements lies in between. I should have put the measurement, sorry. So it lies in between. So that's a good point for us. So at initial stages, the comparison with star measurements advocates for a finite baryon transport due to the string junction, but not for the electric charge. So we have different baryon to electric charge stopping. And at final stage, I'm sorry, I really wanted to have some pretty beautiful results, but I still have some very preliminary results for that. So if you consider final stage or after the hydrodynamics and afterburner, particularization afterburner and everything, in the two same situation compared to the exact same data, we have this green curve and this blue curve here. So you see that there is an increase, and this remains to be understood. I mean, we completely rethink this, and I think the result will be much better, but still, we see a significant difference between those two. And here, just for consistency, I show the results at initial stages. So when you see that the impact of the hydrodynamic, and basically this can be understood as when the hydrodynamic is running on, you have less, so you have, so to say, a motion of the baryon number and electric charge towards the midrapidity, because it's kind of diffuse. So this increases the ratio differently or the same, and we have to measure that in detail. But still, we have a difference here, and then the comparison to star measurement at final stage, shows a significant decrease of this R1 ratio for a finite baryon transport and not for the electric charge. So this was my last slide, and this brings me to my conclusion.
You have a question?
Let him finish and I can ask.
Okay, you can finish.
Yes, I will finish next time. So this is just to wrap up an outlook, basically. To this question, if this is a triangle or this is a Y shape, we can test it experimentally, but by looking at the way the baryon number and the stops, and especially compared to the electric charge. If the electric charge stops differently from the baryon charge, we can expect that they are not carried by the same object, or at least not traced by the same object. And what we see is that there is a clear difference in baryon and electric charge stopping in isobar 400 GeV collisions at star, and especially we have an excess baryon stopping. And our result with the simulation, which includes the baryon junction as an initial condition, is compatible with the star data for the baryon junction picture. And the ratio that we have, and I try to take some time to understand it in detail, is also sensitive to the neutron scene, so it's interesting for the nuclear structure. But also you have to to think that our results needs to be compared properly with the experimental data, because we have this kind of impact of the neutron skin and everything else. And for this, we just had, for the equation of state in music, we have decoupled net-baryon and net-Q density evolution, so we can think of studying the neutron-rich collision now with this model. And at a short time, I will do some machine learning techniques to increase the statistics that we have here. We want to see what would be the results. And on the long term, as I mentioned maybe earlier, we want the diffusion of the conserved charge. So thank you.
Okay, so yeah, please. So sorry.
Sorry.
Yeah. Hi, really thanks for this nice talk. On slide 24, just a previous slide.
Mm-hmm.
So what causes the green curve to increase with hydro? Is hydro transport having some difference in the stopping between the electric and the electric charge and baryon number, or yeah?
So that's a really good point, because I wanted to say that to you like that, and I wanted to have this question, so I can precise something that we have here. So we have the exact same equation of during the evolution for the electric charge and the baryon number. So there should be any difference, and here we still see a difference here, and for now we understand this as a difference in the way the equation of state that we have during the hydrodynamics, and just at freeze out, is transferred into URQMD after burner. So basically, we lose some electric charge in here, and then this causes these increases. So here the delta Q is the electric charge, and if we lose some particles, we will see an increase. So we are currently calculating recalculating the stuff. That's what I wanted to say also. It's like this result is not, I mean, we don't expect that from the hydrodynamics that we see at ideal level, because if we have diffusion, maybe the diffusion between baryon and electric charge is different, and then we can have this. But at ideal level, we don't expect that so much. So yeah, we are working on that. Thank you for the question.
Yeah, and just the same on the same thing. So if there is a difference between the charge transport and baryon or diffusion, you will exactly see the same thing as in your initial condition, right? Even if you have lambda Q equal to lambda B, if the diffusion causes, this, what you call the jumping to the string, or, this, you will exactly see the same difference, right? So is there a way to distinguish between the two, or like, is there a mechanism by which there can be different diffusion for baryon number and charge in during the medium evolution or transport?
So okay, so first of all, I would just want to comment on this idea of different diffusive coefficient for baryon charge and electric charge. So this is very, very quick. Actually, it lasts for 10 Fermi, so it's very, very quick. And second, from microscopic calculation from Jan Fotakis et al. In Frankfurt, you can access this diffusion and for electric charge and baryon number, and you see that they do not differ from orders of magnitude inside the QGP. So basically, we expect that the diffusion of baryon number and electric charge would be kind of the same. So the idea is that if they diffuse the same way and they have only a small difference, the effect that you see on this ratio will be dominated by the initial condition. But still, that's actually a very interesting question, because I don't have a mean to distinguish, especially experimentally, between those two situations. It can be that there is no baryon junction, and that there is a very different diffusion between baryon number and electric charge. For now, it's not set. It's just that if we forget about the diffusion and that we try with the baryon junction, it seems compatible with the data. But the other side has to be tested. I absolutely agree.
No, I mean the electrical conductivity of the QGP is something not constrained by the baryon transport, right? So that was why it's a property of the QGP, right? And we don't have strong constraints on that.
So what is the question?
No. I'm saying there can be the charge transport and the baryon transport can be different in the QGP, right?
Yeah, I totally agree. And in this calculation from microscopic theory that they did in Frankfurt, they actually have a diffusion matrix in the QGP, and you see that it's different. But my argument is just that they are not orders of magnitude different.
Okay, thanks.
Yeah, so if you have lambda Q equals 0, does that mean you have 0 net charge at midrapidity?
In the beginning.
At the beginning.
Absolutely not. No. It means that we have not extra stopping mechanism for the electric charge. So in the 3D MC Glober, we have at first a probability that the electric charge will be deposited on the string. Like it's the basis.
So your initial cartoons are not realistic. So even without the lambda Q, you have some net charge at midrapidity. Okay.
Absolutely. That's right. Thank you for the comment.
Yeah. Okay.
That's a very good point. Thank you.
Your dashed line essentially is when lambda Q equals to lambda B, but for the initial condition, right?
Yes.
So and then you can see your hydro do transport. You know, you go from dashed to solid line now with the green curve. You do have some kind of transport, like diffusion, you know, charge or barrier through your hydrodynamics, right?
But why is the charge?
No?
Why is the charge transported differently than the baryon? So shouldn't this ratio be independent?
That's the ratio, yeah. But apparently they're transport differently.
Yeah, in the hydro, what does that?
In the hydro.
Where does that come from? That's a good question.
Yeah.
Yeah. So I think this question has already kind of asked during the talk. So I wanted to say that, yes, we have the exact same equation for the evolution during the hydrodynamics. So we don't have any difference between baryon and electric charge. But then we have also a particularization and we have an evolution in the afterburner. And the idea is that then when we translate the particles that we have at freeze out after the hydrodynamics, which respects the same longitudinal, the evolution during the hydro, then we lose some particles, electric charge particles, because the URQMD particle list is different from the particle list we have in the equation of state. So basically we evolve more particles and then we cut this and put this into the afterburner. So
you don't conserve charge at the freeze-out?
We consider charge at the freeze-out.
You conserve.
But in your hydro equation, you should have separate electric current conservation and baryon current conservation equation, right?
We do have it. Yeah.
Yeah.
So that maybe when the initial condition is different, maybe the diffusion will be different.
But for lambda,
the diffusion,
there's no diffusion in there.
There is no diffusion, and the evolution during the hydrodynamic is the same. You have to
it's just like you just said the equal in initial is equal stopping. Yeah.
Yes, and it remains so in the hydro phase. My understanding is once you particleize, then, and that's what I want to understand. You say you lose particles. That means you don't conserve charges at the particularization.
So to be honest, I think no, because the particle lists are different. So basically, the what we will afterburner in the URQMD will be less particles. So basically, what we will have at the end of that will be less particles. So I don't think it's in the particularization procedure, but more into what we consider or not into this afterburner. So what we did is that we recalculated the equation of state to be consistent with URQMD, and we are also studying the as if there are no afterburners. So basically, we do the freeze out and the decays, and then we just do the measurement of the particle. That what we have here. And in this sense, we did some preliminary tests, and we see that there is not much difference. We still miss some electric charge, but it can go out also, or it can go. I mean, this is the charge conservation is given at a certain percentage. It's not absolutely conserved all the time. This is something that has to be controlled. Yeah, but yeah, in the end, it's very negligible, so to say. So yeah, this was an issue in these sets of results, and I'm happy that this question came out because it allows me to precise this kind of discrepancy. That's the reason why I show it here also. So yeah, we have what you say, initial condition, hydro, everything is the same, but then we have some difficulties into the last stage of the evolution with that.
Okay.
Yes. Yeah. Hi. On the y-axis, when you compare with star, is the effect of resonance play any role? Is it considered from the star data, or how do you think it will affect?
I'm totally confused.
I think it's I think it's considered. Yeah. Like,
it is?
everything is included in the star data. I'm not sure, but I think everything is considered here. Yeah, I had this.
And the yield they do the theta. Okay.
So there was no correction. Yes, no correction for the decay. I think in this data.
They include the filter. Okay, no question. Let's thank Rudra again.
Thank you.